All right. Well, what does this algorithm actually look like? We'll call this the general algorithm for connectivity, and then we'll look at a few specific implementations of that over the next couple sets of lecture slides. All right, well, you're given a graph, and you always have to be given a start vertex here, because as we said before, if you start at F, you find different things, you're connected to different things than if you start at A. So our algorithm is always going to take G and a start vertex. Well, let's mark things as not found. So this is my dictionary notation, or my map notation, of setting every vertex equal to false inside of a variable called found. So we're going to say they're each not found to begin with. So that's for every vertex in my graph's vertices. We'll start by marking the start vertex as having been found, and then we'll grab out edges. So get valid edges, and again, valid edges are an edge going from a found vertex to an unfound vertex. So that would be all of these edges shaded in orange here. So the AC edge, the BC edge, and the BD edge. So I'm going to find one of those, and if for some reason I don't have any valid edges, that would mean that that function get valid edges didn't find anything, so I'm going to break. Otherwise, I'm going to just mark that vertex as having been found, and that's the end of my algorithm here. So that's a very general purpose way to do what we just talked about. So start at S, it finds A, and then it finds B, and just marks them as found, and so on. It does require us to have this sort of special function here that can get the valid edges, and we'll spend some time the next few lectures talking about ways to do that. All right, so let's do a quick proof of this. Does this actually work? So my claim here is that at the end of this algorithm, if a vertex is found, then there exists a path from S to V. That was our sort of our definition for two vertices being connected or being findable from one another. Let's do this by a pretty quick proof of contradiction. Let's suppose that the graph has a path from the vertex S to the vertex V. So we have our vertex S, and somewhere down the line, we have a vertex V. So maybe somewhere in the middle there, we go to X, and then we go to Y, and maybe there's some vertices in between, and then we get to V. So that's the path P. The entire thing we'll call the path. So let me put that in orange. Now let's suppose that upon the completion of this algorithm, V was not found. So V being not found means that our connectivity algorithm didn't find it, which means the graph, the two vertices are not connected. Well, that means that one of these edges, somewhere along the path, has to have a vertex going from U to W, where U is found and W is not found. And this is a contradiction to the termination of our algorithm. So what do I mean by that? Let me just start by showing this picture again. We have our start vertex, we have V, so start vertex, and then V. We have to have some edge, so UW edge along this path, where U is found and W is not found. It doesn't matter which one it is, but for V to have not been found, that has to be the case. So why do I say that's a contradiction? Well, we're going to assume here that our get valid edges will always return any such valid edges, and this edge here would have been a valid edge that it would return. So that's a contradiction. All right, well, let me set up the next lecture. So how do we choose the next edge? We have a bunch of vertices that have been found, we have a bunch of vertices that have not been found, and we have a bunch of edges connecting from found vertices to not found vertices. How do we pick a specific edge? Well, we'll look at two commonly studied options. First is breadth first search. You can think of this as exploring the graph in layers. We're at our start vertex, and then we look at everything that's 1 hop away, and then everything that's 2 hops away, everything that's 3 hops away, and so on. If you want to anthropomorphize this, you can think of this as a cautious exploration. And this will use a FIFO data structure. And just to see if you're paying attention, what's your favorite FIFO's data structure? Well, if you remember what FIFO stands for, that's first in, first out. So this would be a fair data structure. If you're the first in line, then you're the first served. And a lot of times we'll call that a queue. So that would be your FIFO data structure. A depth first search, on the other hand, is going to explore recursively. So it's going to jet out as far as it can, and then backtrack, and then jet out again, backtrack, and jet out. And then this is a more aggressive exploration that backtracks when necessary, and it'll use a LIFO data structure, which would be something like a stack, or it would just use the recursive call stack. All right, let me go back to the very beginning, and we'll look at this animation again. So knowing what you know about breadth first search and depth first search, see if what's going on in this picture sort of makes sense to you. You know, breadth first search exploring in shells, and depth first search jumping out as far as it can recursively and then backtracking. So I'll go ahead and let the animations for Dijkstra's and A*STAR play out one more time, and then after the breadth first search and depth first search animations, this video will be over. I like to think of breadth first search as sort of a amorphous blob extending out from the start.